Hey guys, what's up? Eddie Aho here with KissAnalog.com. Hey, today we're going to get back into switching power supplies, switch mode power supplies, SMPS. So we're going to get back into this with the PFC converter. Okay, we have to finish off that PFC design so we can move forward. So I'm looking at, after the PFC, I'm looking at either an LLC converter or, I don't know, an active clamp forward converter. Not sure. Here, let's pull up this whiteboard. I want to show you guys something. Okay, so on the PFC converter, power factor correction, right? Active power factor correction. Because there are passive power factor correction circuits been around for a long time. Now these PFCs been around a bit, but unfortunately, God, I've been trying to buy power supplies for audio type stuff, and I want the LLC converter because they're low noise type converters, but I want it powered at the PFC, the front end. And a lot of them are the low frequency switchers, just a bridge rectifier with a capacitor, like we've been studying in the other videos. So I really did a lot of videos on that, so you have a really good feel about that. And on PFCs, I think I've done like 17 different videos on different types of PFC videos. But on the design ones, I've done a few on the inductor. That's the heart of pretty much any converter, is the magnetics, whether it's a transformer or an inductor. So we did a lot on that and how to choose that. I still have one more to kind of tie the loose ends up. I'm going to do one video where I just go through, select all the components, size them all, and all that kind of stuff. And when I do that, you'll have the background of all these different parts and why I chose what I did. Okay, so today what I want to do is I want to show you some waveforms here. And I want to show you this capacitor, the input capacitor. If this is just a typical boost converter, that would be a bigger cap, would be a bulk capacitor, that when this guy switches on, this capacitor right here would provide that high frequency current, that close proximity, capacitance to allow this guy to pull current into that inductor. And then, then when it turns off, the current continues going through the inductor and it comes out the diode. But in a power factor circuit, instead of having DC over here, we have a pulsating DC, right? So the pulsating, it's, it's two halves of a sine wave, okay? This capacitor cannot be too big. So we can't just size it big enough that this guy has a well, to pull current from. It has to be sized so that it keeps the integrity of that pulsating DC current. Okay, so we don't want to screw that up, because the point is we want to pull, as this guy switches on and off, we want to pull little slivers of current through that pulsating DC so that the current waveform, when you integrate it, it looks like the same thing, same shape. That way we get the same power factor. The power factor is close to unity. That's what we want, okay? Now the thing is in a switching power supply, you're going to see noise, high frequency noise. A lot of that noise is low energy. Unlike the low frequency switchers where there's so many harmonics and there's so much noise, that stuff is unusable, and it takes part in how you calculate power factor. It's not just a phase shift of the current and the voltage, because now the current doesn't look like the voltage in a low frequency switcher. In a high frequency it does. So the bulk of the current is in phase with the voltage. That's why the power factor is so good. There is noise, and that takes away from that power factor. But on the other hand, there's so little that for EMI, it's actually easy to filter, okay? So it's not, so that's why we want to see a PFC in front of a switching converter with the isolation for the output stages, because this is just a boost converter, okay? It's just getting the voltage ready for that isolation stage. So that's what the PFC is doing for us. And to do that, so on a product where you have that switch that switches between 120 and 240, that's not going to be a PFC front end. That's probably going to be a low frequency front end. So you have to tie the capacitors different so you get different voltages. So on a PFC, the voltage over here could say 120 to 240. So 120 might drop down to 85, 240 might go up to 265. The peak of those waveforms, as those pulsating waveforms come through, we want to always be boosting. So the voltage here has to be higher than the peaks over here, okay? That's why a lot of times 380, 390, 400 volts is chosen. On this eval card that we have from Texas Instruments, they have 390. So that's a good voltage, okay? So we're going to have 390 over here. We're going to look at that voltage. We're going to look at the ripple on that voltage too. And we'll look at the current out here too. We're also going to look at the current coming in to see if it does look sinusoidal, to see if we did maintain that, sinusoidal current, okay? But this capacitor, we want to focus on this. So this capacitor, when this guy switches on, he's going to pull current off that capacitor. So that capacitor is going to discharge, and then he's going to charge up, and he's going to discharge. And we want him to be a high frequency enough capacitor where the low frequency pulsating currents, he doesn't interfere with that. But he does provide enough current for this. I'm going to show how you do the calculation for that in the next video. It was going to be too long to do it all in one video. So today we're just going to look at some waveforms. So let's jump over here and do it. All right, guys, so this is the setup. Let me just walk you through it, okay? Here's a PFC converter, right? So at our input, well, I'll just show you the wiring. We're being powered by this guy right here. All right, guys, we're being powered by the IT7321 300 VA power source, okay? So sorry about the flashing. It looks great in person, but anyway, we're coming through here, and I do have a current probe hanging off here, okay? So we're coming down here to the input, and the input power goes right, well, here's power cord, whips back around, comes right into here, all right? And then there's a little bit of an EMI filter, fuse EMI filter. So we got some X caps over here, a little NTC here, which is an inrush current protection. And then over here we have 12 volt supply. I'll show you that in a moment. Then under here we have differential probes. They're going up under here. What they're doing is they're looking at the voltage across this capacitor. This is the capacitor that's the final capacitor feeding the PFC, okay? So we're going to show you that. And that's the capacitor we want to see the value. And by the way, this one says it's a 0.33 microfarad, okay? 275 volt poly cap. And then here's our inductor, okay? And our switching transistor is right over here, and the diode is right here, and the bridge rectifier is right here, okay? So, yeah, looks fairly simple. On the other side of the board, so I have another board right here. On the other side, we see all the control circuitry right here in the middle, okay? There's no isolation. It's just a PFC converter, okay? So it's 390 volt DC coming off, okay? And it comes around here. I got all the wires twisted everywhere. And it comes to the input of this Vicor module, okay? This DC-DC converter. Vicor makes all these really nice small modules. So we have a nice little Vicor here. And it supplies, it'll go up to 300 watts. Here, let me just show you the label there. If you can read the label, it's 375 volts in nominally, and it's 300 watts output, okay? 346 watts on the input, 12 volts on the output. So right here, we're going to see 12 volts, and here, I'll just show you something. The Vicor has the output with the sense, so you have to tie the sense together. So I have shorts between the sense wires and the output, and that's so that you can run the sense wires separately so you can account for the voltage drop in your output wires if you need to. So up here, I'm using the Voltcraft, the VC870. By the way, these are all awesome multimeters. I just wanted to show them off a little bit. This multimeter here is reading the 12 volt output, okay? This one right here, this Amazon, which you can't get the Amazon commercial anymore, but people pointed out in a video I did that, well, there's a couple different people making this thing, and one of them, I will put the link down below, okay? But it is, all right, here we go. Just had to grab this. Southwire. So Southwire makes these really great meters, but now that I'm thinking about it, I'm gonna have to look this up. I think these are all made by CEM, who makes this one. And so yeah, so Southwire, you can get that meter in a Southwire brand, and it's just over $100. I'll put the links down below, but man, these are just great meters. So anyway, then over here at the input, I'm looking at this 12 volt right here, and I'm coming up here to this KPS. KPS is a new meter I found. Awesome meters, okay? And they go by another name because the parent company owns a couple different companies. But anyway, KPS, awesome, okay? So we come over here and, oh, I'm using the Testo, another meter I really like just for probing and touching things and whatever. This is a great meter, guys. Fantastic meter, okay? So you electricians or whoever wants a good, safe meter, there you go. All these meters I've shown you fit that category. But we come up here to the WampTech. And I got 11.5 volts, and I actually have it activated right now. See, turn it off. It's set for 10 amps. I don't need 10 amps, so I'm going to come over here and drop this down to 1 amp. So if it short circuits, something happens, that's going to be bad, but at least it won't burn up traces like 10 amps would. So there we go, 11.5. See, hardly any current at all. So I could set it for half an amp or even less. All right, so then over here, I'm going to use the MixSig. It's just so easy to use. It has all these nice probes. So we have this differential probe right here, looking at the voltage on this capacitor right up here, okay? That's the bolt cap. We're going to look at this little cap feeding the switcher, okay? So can it feed the switcher the current that it needs without sagging the voltage down? We're going to look at that, okay? So then the CP503, that is this current probe, which I'm going to move because I have it on the input. I don't need it there. So I'm going to move it over here. And the arrow is pointing that way, so the current plus is going this way. So that turns out to be the right way to put it. So I'm going to look at the current going out to this module. We want to look at the voltage and current right here, okay? So this differential probe, this guy right here, the MDP 1500, another awesome differential probe. It comes up here to this guy. It's powered by USB-C, and we're going to have that on the 500X range, okay? And so there's the current probe you already saw, the one I just moved. That's this one. This one here's the differential probes you saw right here. Now the RCP 500, that's this guy, okay? So he's kind of hanging out here on this guy right here. So he's going to show us the current coming in. And there's a quick preview, but I'm going to grab my iPad because that way I can show you the waveforms really clearly and all that stuff. So it's another reason I like to use this MixSig for that reason. And I just wanted to point out, in case you've noticed, there's 4.9 volts hanging out right here. Okay, so the output of this. Why? Because that bulk capacitor is just sitting there. Now, so when you design one of these, you might want to put a resistor in parallel so that over, say, a minute, something, if you know that you could drain the capacitor so it goes down to 0, so it's safe. If you put too small resistor, drain it too quick, of course, it's going to have to be a power resistor. But, you know, a minute I would think is reasonable. So, yeah, a resistor in parallel would have saved that because this guy doesn't have enough voltage to turn on, so he's not loading that down. So it's just kind of hanging out here, 4.9 volts still. And it's been a while. I've been running around doing things, and it's just slowly discharged down to that. All right, guys, so here is the MixSig screen. Okay, so I've got all 4 channels hooked up. Channel 1 is 25 volts. You can see at the top right corner, 25 volts per division. And it's times 500, okay? That is going to be the differential probe, the DP750-100. And you can see I've got the marker down here at right there. You can see the marker down there. The left column changes depending on which channel I select. So 0 volts is down there, and it's called VAC input. Okay, so I labeled it that way. Okay, channel 2, I just clicked that. So now you can see it in the center of the screen, 0 amps. Now it is reading current. It's going to be the CP2100B, okay? And that is 500 milliamps per division, and it's times 10 position. Channel 2 is sitting on channel 4, so I'm just going to show you channel 4. See now, 4 highlighted over top channel 2. I wanted them in the center of the screen, and it's 100 milliamps per division. It's the other current probe, looking at the current going from the PFC to the DC-DC converter, okay, the Vicor. Then what we have is, let's go back to channel 3, I skipped. Okay, so you can see its zero reference point is where it sits, and it's called V secondary. So by the way, did you notice what I labeled these things? Channel 1's VAC input, channel 2's IAC input for current AC input, channel 3 is volt secondary, so that's the 400 volts or 380 volts coming off. Well, it's 390 volts coming off, so that's the V secondary. And then channel 4, the green one, is I secondary. So that's the current coming off of the 400 volts. Well, I keep calling them 400, but 390 volts. All right, so let's go ahead and power this thing up. Got to turn my multimeters on so I can watch the voltages and everything. All right, so here we go. We're going to go ahead and power it up. I have 0.1 amp load on the 12 volt output. It came up at 385 at about 70 volts in. So I'm taking it up to 120 volts. So we're at 120 volts, and you can see all the waveforms kind of going on. Well, it's kind of hard to see them, but here I'm going to crank on the current. Okay, so there's 1.1 amps, it's 24, almost 25 watts. When at 2 amps, that's 40 watts. 3 amps is 54. 4 amps is 67. And 5 is 81. So we're at 6 amps output, 6.1, and we're 97 watts. I'll go 112 watts, okay? So 112 watts. I'm going to go ahead and freeze that so we can look at it. And then I'll drop down the current, turn off the power, so I don't have to worry about that stuff while I talk to you. All right, so let me turn off the green one. It's the current on the 390 volts going to the Vicor brick, okay? So it just looks noisy. When I zoom in on that, it'll make more sense. So I'm going to turn it off for now. Okay, there's our waveforms, okay? Now let me go ahead and turn off, I'm going to turn off the blue one. We're going to just start by, you know what, I think we'll start by just looking at these two things right here, okay? So the yellow one is the voltage on the capacitor that we're interested in sizing, okay? Which what I'm going to show you how to size. And it goes from 0 to about 175 volt peaks, something like that. And it looks like it's 114.3 volts RMS, okay? So, and it looks so noisy on top, right? We're going to zoom in that. I'm going to show you that. Channel 3 is the 390 volts output, and it says it's about 386.3. And it looks like it might have a little waviness, and it's kind of hard to tell. It's a little, you know, maybe not super clean waveform, right? Okay, so let's go ahead, zoom into this waveform. Okay, I'm going to move it over here in the center. Okay, there we go. So now, if you look at the voltage, the 400 volts or 386, looks pretty solid, right? Now, where you see the little spiky things on the yellow waveform, channel 1, you can see a little bit of a fuzzy spikiness on channel 3. So you can see a little bit of stuff there. So that voltage that's on that capacitor looks like it just has a little bit of ripple. It's 25 volts per division. So it looks like it's, you know, 1, 2, 3. So it looks like it's about, I don't know, 40% of a division. So it's not very much, right? It's about 10 volts peak to peak, I'd say. Okay, so that's all the ripple we're seeing on that capacitor. So it's not being discharged too much between pulses, right? And then when it does turn, you can see when the FET turns on and off, you get these, you know, these switchy noises. And I'd almost say where it turns off is where you get the bigger spike, and then where it turns on is a pretty small spike. It's even difficult to see. We'd have to zoom in on that to see, right? All right, so you know what? Let me zoom back out again. Okay, and I'm going to turn on the current. Okay, so this is the current going into the power supply, and it's sinusoidal. It's got some noise on it, but it's sinusoidal, right? It's not that pulsating DC is, or pulsate. It is not that pulsating current you see on the low frequency switcher. It's a little noisy, but it's sinusoidal, so that's great for power. The power factor is going to be awesome on this. Okay, now, and you know what? I'll do it again and I'll read off the power factor. I forgot to do that. But, okay, here. Let's go ahead and zoom in on this again, okay? And actually, you know what I'm going to do? I'm going to move over a waveform where we have a peak, you know, where two peaks are together. Okay, now there you go. So you can see the current, it's pulsating, charging, discharging with that ripple voltage. So, pretty cool. That's where that's come from, and we got some high frequency noise. This high frequency stuff is a lot easier to filter than low frequency, right? There's not near as much energy in it. Now, in the blue waveform, in the current waveform, right where it crosses zero, that's where you see kind of a noisy thing occurring, right? And that's because, you know, when the voltage goes near zero, you can't really get any current. So there's kind of an off and on period there, and a recharging of the inductor as it starts to charge back up and starts to do its thing. So that's, you know, crossover distortion in a PFC converter. But percentage-wise, it's not nearly as much noise as a low-frequency switcher with diodes, with pulsating currents, where the current amplitudes, the peak current amplitudes, are easily 4 times bigger than the RMS. Where in this case, the RMS is 890 milliamps, and these peak things are pretty small, right? Let's zoom in on it again. Now, over here, it's 500 milliamps per division, so each one of those small grids is 100 milliamps, so it's like, you know, what is it, 100? Maybe 150 milliamps peak to peak, so it's pretty darn small. Now, if we want to zoom in on the kind of the nasty part of it, let's do that. Okay, so even that, so 500 milliamps per division, so even where it's swinging, you know, where you can see the bigger ripples, that's still only not even, that's maybe a half a division, so still it's only 200 or 300 milliamps peak to peak. It's also higher frequency stuff, which again, a little easier to filter, okay? Well, a lot easier to filter. Okay, let's turn on the current off the 390 volts. Now that looks pretty bad, right? Let's zoom in on that again. And really what it is, now this guy's 100 milliamps per division, so it's 1, 2, 2.5 divisions. So it's like, you know, 250 milliamps peak to peak noise. Okay, 250 milliamps. The RMS current is 273, okay? So you see the current, it drops down to about 100 milliamps, and then it ripples up to about 300 and something. So you got about, you know, 200 milliamps of ripple on that. So again, we can filter this out with some LC filtering on the output and some other capacitors and so on. But yeah, it's not very much current, and that's because the voltage is 390 volts. So that's the beauty of it, is you have high voltage, low current. Okay, so yeah, we can clean up this current too, and you know, that's not going to be hard at all. Okay, now the voltage waveform. Here, let's go ahead and AC couple that, okay? Let's AC couple that, and then we'll zoom in on that. Okay, let's go recapture that and see what that looks like again. Okay, and I'll read the power factor this time. I'll remember to do that. So let me see, turn that on. Okay, we're bringing the voltage back up again. Okay, we're 120 volts. We have 385 volts on the output from my meter. And I'm going to turn on the load. Whoops, it already was on. I just got to crank it up. Okay. And power factor is 0.94, by the way. We're at 68 watts. And, Okay, there's our 112 watts and power factor is 0.997. So that's pretty darn good, right? Okay, let's go ahead and freeze that. Okay, I'll bring down the voltage and that way I can talk to you about this. Let's see what we're seeing. All right, so we're looking at the kind of the magenta waveform, right? Kind of the pinkish one. And now it's 2.5 volts per division. And so we can see that it's only going up. Here, let's zoom in on it a little bit. All right, so it's going, I don't know, you know, you've got the noise on it, of course, but it's going, it's a little bit more than 3 divisions maybe. So right down here it says 1.2 volts RMS. Okay, so 1.2 volts RMS. Now let's zoom in on that closer. You actually can see like where the current's charging the capacitor on the output. So you get the little ripple there, the little triangular ripple, and you get little switching spikes. These spikes are really low energy, just high frequency, but low energy. There's not any energy in them. They're just little teeny spikes like that. See those? Real high frequency, but yeah. So there we go. So that's what the ripple looks like on the 390 volts. It's 1.37 volts ripple. That is pretty darn small. All right, guys, so let me know what you think, okay? Give me your comments down below. Did you like this? We're going to calculate the value of that capacitor. It's going to be fairly easy. And we'll probably, we might look at some more waveforms just to kind of show how the calculation and the waveform looks together. But yeah, it's an important capacitor. But yet again, it's not that hard to deal with. Once you know how to calculate it, once you see what it does, it's going to be really easy to pick it in the future, okay? You can just kind of, you'll get a feel, oh, we're doing this much power, I probably need this much capacitance. So it'll be something like that. But if you want to calculate it, it'll be easy enough to do, but you'll have a lot of confidence that you know that that capacitor is going to be okay. So, all right, guys. Hey, 2 thumbs up to my patrons as always. Thanks so much. And 2 thumbs up to my YouTube members. You become a member by just hitting the membership button down below. I think I've got 9 now. That's pretty amazing. And 2 big thumbs up to Danny. He's a team member. Way to go, Danny. Thanks. And 2 thumbs up to the guys that have hit that super thank you button, bought me a cup of coffee, or even a beer for a rant. So, appreciate it, guys. Thanks for watching. And hey, subscribe if you haven't done so. That's a great way to help the channel for free. It helps a lot. It's unbelievable. Appreciate it. And thanks for watching. Comment, all that stuff. See you next time.